Greetings everyone. Let's work on some partial fraction decomposition so that we can find antiderivatives. So an example of where this could be seen would be when we have to evaluate an integral that looks something like this. Now, we should have already considered using techniques that are more elementary, more simple than partial fraction decomposition first perhaps, like trying to do a substitution or some other first semester technique. In this case, it doesn't work. If you try to substitution here, you're going to get in the denominator here, if you let that equal u, your derivative would be 2x minus 3. And although the numerator has x in it, it just doesn't work out well for doing a substitution. And so we're going to want to do partial fraction decomposition. The idea behind partial fraction decomposition is just so we can algebraically rewrite the integrand into a more useful form for us to find the antiderivative, or something more simple. So what we need to do is we need to take that fraction, which the rational expression, the x plus 1 in the numerator, we're going to factor the denominator. Hopefully you see it as x minus 8 times x plus 5. So in trying to be efficient here, I'm going to just get to the factoring immediately. And then we're going to break this down into two fractions where we want to learn the numerators. The first one has a denominator of one of the factors, x minus 8, and then the second will have the other factor, x plus 5. Now from here we just need to find the values of a and b. And so to do that, we're going to clear the fractions here. If you multiply both sides by the denominators, you're going to get x plus 1 over here, and then you'll have a times the quantity x plus 5 plus b times the quantity x minus 8. Make that clear. Now, just to make sure, for those of you watching the video, that we know what we're talking about, I'm multiplying this right side here by the quantity x minus 8 times x plus 5. You gotta squeeze it in there. And I'm doing the same thing on the left hand side of the equal sign also. It's kind of hard to squeeze in there. I didn't leave myself a whole lot of space. And of course I've already made a little typo. It should be a minus sign here. X minus 8 times x plus 5. So what that does on this side, that's going to cancel completely all of this stuff out over here. But on the right hand side, when I distribute the x minus 8 and the x plus 5, the first fraction will cancel with the x minus 8s, leaving just an x plus 5 times a. Second fraction will leave the x minus 8 times b, because the x plus 5s will cancel. Now from here we just need to figure out values of a and b by choosing convenient values of x that will help us get rid of some of these terms. So if I let x equal 8, then the term involving b will cancel. All of this will become 0. And so I'm going to get a plus 1 is 9, a times the quantity, a plus 5 is 13, so a is going to be 9/13. Similarly, if I let x equal negative 5, then I'm going to get negative 5 plus 1 is negative 4, and then I'm going to get a negative 13b, so b is going to be 4/13. And these are the values that I'm going to use to rewrite the integrand in the previous screen. So now when I do this, I typically just use 1 as my numerator. Let me go back and make sure I got these values here. So I need 9/13 for a, and that's over the x minus 8. So I'm going to go 9/13 times 1 over x minus 8. One last double check. Yeah. Plus 4/13 times 1 over x plus 5. The reason why I do it like this is because, by our constant multiples here, constant multiple rule, I don't really need to worry about the 9/13 and the 4/13, because when I find the antiderivative of the 1 over x minus 8 and the 1 over x plus 5, they become the natural logs and simple to do, and then I just kind of multiply them by those constants. So working this out, we get 9/13 natural log absolute value of the quantity x minus 8 plus 4/13 natural log absolute value of x, the quantity x plus 5, and all of that plus our constant of integration. So there's an example of the partial fraction decomposition. So here's another example. What you should do right now is you should pause the video and go try this one on your own and see how far you can get. You'll always come back to the video to check your work or to see if you got the right answer, or if you get stuck, to see how you can not get stuck next time. But really the benefit comes from you actually trying this on your own. So pause the video, go work this out, and then come back and check. So hopefully you were able to have some success when you work this out. You factor the denominator. Whoops, not 9. It's 9 minus x squared, so we're going to need a 3 minus x and a 3 plus x. And then we'll create our two separate fractions here. The letters you use in the numerator are your own choice, really, as long as they are not already being used in the problem. But this is how this is working out. And all pretty straightforward algebra here, I hope. So now if x is equal to 3, then we're going to get 5 is equal to 6a. And so a is going to be 5/6. And if x is equal to -3, then we're going to get -1 is equal to 6b. So b is going to be -1/6. Alright, you just be careful that when you go put these values back into your fractions, you put them with the right one. A is 5/6. That goes with the denominator of 3 minus x. And b is -1/6, then goes with the denominator 3 plus x. Some students don't pay attention and they put them sort of randomly, which, and sometimes they get it right, sometimes they get it wrong. So let's try to control, the outcomes here and make sure we're paying close attention. So 5/6 goes with the denominator 3 minus x. So when I rewrite this, I'm going to have 5/6 and then times 1 over the denominator 3 minus x, and then -1/6 times 1 over 3 plus x, or x plus 3. Now I'm switching them back and forth. I'm just going to go double check to make sure I didn't screw that up. And minus x, okay, so that looks good. Now I did throw in a little bit of a curveball here, so hopefully you saw it. And that curveball comes in with the antiderivative that you have to find. There is a minus sign in front of the x in this term. So you can either do a little substitution, for instance, letting u equal 3 minus x, and then working out the rest of it, or you can do the substitution mentally. What has to happen is our antiderivative has to have a negative to balance out the negative that would be from taking the derivative of the antiderivative and having to multiply by the negative through the chain rule. I'll show you that in a little bit. Let me get back to this problem first. And so we're going to get 5/6 times negative. I could put the negative in front of the 5/6, but I didn't. Natural log of the absolute value of 3 minus x. And then -1/6 natural log of the absolute value of 3 plus x. And then all that plus c. In case you wanted to see that, let's just isolate if we were finding the antiderivative of 1 over 3 minus x on our own, or on its own, and we wanted to do that. The substitution would look like this. We would let u equal the quantity 3 minus x. du would be equal to negative dx. And so we would replace dx with negative du, like this, and so we'd have the negative of the integral of 1 over u du, and that of course would be negative natural log absolute value of u plus c, which of course is negative natural log the absolute value of the quantity 3 minus x plus c. So that's how that part worked out. It's good with practice if you could start seeing some of the simple u substitutions done in your mind, so that you don't actually have to write all the steps down. But by all means, if you need to write the steps down to make sure you're accurate, go ahead and do so. So here's another partial fraction decomposition example. Well, there's an issue with this one here that hasn't come up in the previous two examples, but we need to be aware with. The process of partial fraction decomposition requires that the degree of the numerator be less than the degree of the denominator. So in looking at this here, the degree of the numerator is 3, the degree of the denominator is 2. It's always the highest power. So since now the degree of the numerator is not smaller than the degree of the denominator, we need to do long division to rewrite this first before we can do our partial fraction decomposition. So keep that in mind as we move forward with this example here. So let's get a new screen here, and we're dividing x cubed. I gotta go back and look. Plus 2x minus 1. So I have 0x squared, so I'm going to put that in here. Plus 2x. I think it was minus 1. Let's go check. Yeah, minus 1. And then we have x squared minus x minus 12. Now, if you struggle with the long division, let's walk through that really quickly so that you can, be better with it. So you always got to look at the highest power here, and then go to the highest power here and ask, what do I need to multiply x squared by to get x? Another way of saying that is what is x cubed divided by x squared? Of course, that's just going to be x. So we're going to go write the x up here. Now that x needs to be distributed now to every single term, excuse me, that we're dividing by. So we're going to get x cubed minus x squared minus 12x. That looks terrible. Just want to separate that a little bit. Now, the long division algorithm says we have to subtract. The x cubed minus x cubed is going to cancel. 0x squared minus negative x squared is going to give us negative 45.